Medical Cost Prediction, Group 4, by Matthew, Megan, Jacquelyn, and Ning. The main purpose of our analysis is to understand the concept of the multiple linear regression model, grasp the interaction strategies, using the given data to find the multiple linear regression model, and utilize the model to do prediction for the medical cost. In this project, there are two criteria for us to select the best multiple linear regression model. One is the adjusted R-squared value, the other is the p-value. It's a small difference from the simple linear regression model. In simple linear regression model, the R-squared will use the multiple R-squared is also called R-squared value. After loading our data in the RStudio, at the first glance, there are 7 variables and 1338 entries in the data frame. Charges would be our response variable, and 3 categorical variables, sex, smoker, and region. 3 continuous variables, BMI, age, and charges, and 1 discrete variable, children. In this slide, it shows the summary of our data. In this slide, I did the histogram plot and side-by-side box plot to demonstrate our data. In this graph, we can see the relationship between the variables. It's obvious that the BMI and the charges have a linear relationship. In the steps of cleaning data, we checked the missing values from the data frame. Luckily, we don't have any missing values in the dataset. We also removed 6 extreme outliers in the data frame, but after another round of analysis, the outliers don't have enough obvious influence to our result. We also converted the categorical variables into the factors. In our model file, we transferred the BMI data from the continuous data to the categorical data.
And next, we're going to go on to finding the multiple linear regression model. And here I outline the general steps that we're going to go more in depth on in a few seconds. First, we start by analyzing the data, which Ning went over earlier, including the different variables that are inputs, which are the region where they live, their gender, whether they're a smoker or not, and then their body mass index, their age, and how many children they have, which all impact their medical expenses known as charges in this data set. For cleaning the data, we didn't have any missing data, but we did have to remove 6 data points that were outside 3 standard deviations from the mean, making it a right-skewed data set. And after we removed those, it became 1,332 observations remaining. Now, by analyzing the variables, we can see that the gender and the region are both relatively normally distributed with a little bit of variation. But then we can see that the smoker variable definitely has a correlation with charges for being a smoker would mean that you have a lot more medical costs. And as we can see with the correlation matrix down there as well for the continuous variables, we can see that age and charges have a very high correlation, and then BMI and charges have a pretty moderate correlation at 0.19. And we can see for the age to charges graph, we can see that it's a little bit more than linear with a curved line, so it becomes polynomial. And then BMI to charges has 2 distinct groups of data points, below and above 30 BMI. To train the data, we split the data into a training set and a testing set, with the training set being 80% randomly selected from the clean data and the testing set being 20%. And once we go on to the building the model, we start with our original model, which includes all 6 of the original input variables and contributing to the charges model. And as you can see, it starts off pretty accurate at an adjusted R-squared value of 0.74, with all things considered, with no changes. However, we can see that the sex and the region are not statistically significant, meaning that their p-value is above 0.05. So in order to improve this model to the real-world model, we remove those variables that are unnecessary or insignificant to the model, meaning that they would be random. So we are left with BMI, age, smoker, and children in this model. And while it doesn't improve the adjusted R-squared value very much, it does remove those statistically insignificant values, which keeps our integrity for this model. And as we started exploring to improve the accuracy of this model, we came to a few different conclusions. Namely, with age, we had to change that to be a polynomial value instead of being a linear variable, because as age increases, the medical charges increase exponentially. Similarly, we also had to change BMI to BMI2, to where BMI would be a categorical binary variable instead of being a continuous one, since there were two distinct sets of data points, above and below 30, being the obesity line in this case. We also wanted to add the interaction between the BMI2 and the smoker variables in order to show that in a real life scenario, if you are both obese and a smoker, that would increase your medical cost dramatically. And now when we ran this model, we actually did get an improved adjusted R squared value of around 0.86 instead of the 0.74 we were working with before. But it does leave BMI2 by itself being statistically insignificant. However, when we look a little bit further, we do see that the interaction between BMI2 and the smoker variables is very statistically significant and obviously improves the model's accuracy. And once we test the models, with both the real world model and the exploratory model being tested, we can see that the error rate for the real world model is between 2 and 5% after multiple iterations of testing. And the exploratory model is under 1% for all of those tests. And now, seeing the results, we can kind of decide between keeping the integrity of our model with the real world model or improving the accuracy with the exploratory model. And as a group, we decided to stick with the real world model in order to keep that integrity of our model.
In order to interpret the model, we ran diagnostics and checked that the model met the 4 assumptions of a regression model: linearity, normality, constant variability, and homoscedasticity. The figure on the left shows the resulting plots after diagnostics were run. The model did prove to have linearity with an R-squared value of 0.7494. This is a fairly strong linear relationship. However, the data did not show complete normality. As you can see by the normal QQ plot, it did tend to skew to the right. Based on the scale location plot, the model just shows some constant variability, but the condition is not fully met. And the model did not show strong homoscedasticity at all, as you can see by the scale location and residuals versus fitted plots. While there was some, the data did not form uniformly around a horizontal line, meaning that the variance between the variables is not the same throughout the data. So while not all 4 of the assumptions were met, the model can still be checked using the testing dataset in order to prove it is efficient and accurate, and that the model does not show bias or it is not misleading. The model will be used to predict medical costs given any value for the independent variables. After trying many different improvements to the original model, we found 2 models that work well for this function. Model 3 had the sex and region variables removed, creating an adjusted R-square value of 0.7494 and all p-values less than 0.05. There was an error rate of 2.51% reported after a test run. In Model 4, the BMI variable was changed from continuous data to binary categorical data, and the age variable was changed to age 2. This resulted in an improved R-squared value of 0.7525, but the error rate was 2.56%, which is slightly higher than the error rate in Model 3. Neither model was biased or misleading, and both proved to be efficient in predicting cost outcomes. However, while the best overall model was Model 4, after considering the huge data in the real world, we felt the need to balance the cost and improvements. We decided Model 3 was the best for real-world analysis. Therefore, Model 3 will be used to predict medical costs given values for the variables BMI, age, smoker, and children.
Possible further steps in the future. This box plot shows the regions by BMI. The 4 regions in this graph are the Northeast, Northwest, Southeast, and Southwest regions. This model has a region limitation. The results may be different in other regions. There are still many other limitations in this model. We need more information and to try other methods to improve our model. We also want to collect information for the model, such as family history, living habits, for example, eating, amount of exercise, amount of sleep, or seeking medical attention, the person's profession, the individual's health status, population growth, cost of health insurance, and much more. Those will be important factors to effectively narrow down what contributes to medical cost.